So we'd like to be able to solve linear recurrence relations that are homogeneous. And by solving a linear recurrence relation, we mean basically if you have a recursive sequence that's linear and homogeneous, you want to be able to find a closed form for that sequence. So to do that, we want to establish a few things. First, we want to come up with definition of characteristic equation. So let's say you have a linear recurrence relation that's homogeneous, like so. Well, that sucked. Can we undo that? Yep. So here, right, this is a typical linear recurrence relation that's homogeneous. AN is equal to C1 AN minus 1 plus C2 AN minus 2 plus C3 AN minus 3 plus so on and so forth, CK AN minus K. This has degree K, right? So the characteristic equation for that would be R to the K plus C1 R to the K minus 1 plus C to the C2 R to the K minus 2 plus C3 R to the K minus 3 and so on and so forth, CK minus 1 times R plus CK. Now this is the associated characteristic equation right here. I don't know, maybe I should put this one in red. All right, that's what the characteristic equation is, the red dude. Now, so let's say you have a characteristic equation, and you want to get 0 on one side, right? So you subtract C1 R to the K minus 1, C2 R to the K minus 2, C3 R to the K minus 3, and so on and so forth, CK minus 1 times R. And CK from the right-hand side, and on the left-hand side you get R to the K minus C1 R to the K minus 1, minus C2 R to the K minus 2, so on and so forth, minus CK minus 1, R minus CK equals 0. So that polynomial, right, that's going to be a polynomial of degree K. If it has K distinct roots, if it has K different roots, let's put those roots in green right here. So you have K different roots, K different solutions to that equation when you set it equal to 0. Well, then the following is true. The linear recurrence relation, this yellow guy right here, this is the recurrence relation. We'll have a sequence solution that is of the following form. The sequence solution is going to be this blue guy right here. So this blue sequence is basically the closed form of that yellow linear recurrence relation. And here, the R1, R2, and so on, RK, are roots to your characteristic equation. And as for these alpha dudes, which we'll talk about a little later, alpha 1, alpha 2, alpha k, these are just some real numbers, and you're going to figure out what these are. These are going to be the coefficients for your closed form, And you're going to find those based on some initial conditions. So we actually want to show how this works. How does this work? Actually do an example here, excuse me. Example, right? Let's say we have solved the following. AN equals 2 sub AN minus 1 plus 3 A sub n minus 2, where A0 is 1 and A1 is 2. So this is just a recursive sequence. So we're given two initial terms, right? A0 and A1. A0 and A1. We're given those dudes. Come on, right? Those are our initial terms, and then we know how to find additional terms based on the recursive definition here. The recursive definition. The recursive definition is in yellow. All right, so let's come up with a characteristic equation. Characteristic equation, what color are we going to do that in? We're going to do that in yellow. So this should be of degree, what? Degree 2. So if you look at your recursive sequence, it ends with an n minus 2. So that 2 is going to be the degree. So your characteristic equation should be of degree 2 as well. So you're going to have what? R squared. That's going to be on your left-hand side. And then your right-hand side, you're going to use what? 2r plus 3. R squared equals 2r plus 3. Now to solve that, you would what? Subtract 2r from both sides, subtract 3 from both sides, get 0 on the right. And then let's find all the roots. So if I factor, I can do 2 parentheses, 2 pairs of parentheses, r times r to get r squared. Find 2 numbers that multiply to give you a negative 3 and add to give you a negative 2. How about negative 3 and positive 1, right? Negative 3 and positive 1. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. You set your factor is equal to 0 by the zero product property. And you get 2 solutions, 3 and negative 1. So these are your 2 distinct roots. You can call them your R1 and your R2. I'm just going to call them 3 and negative 1. Okay, so you get your characteristic equation. So, characteristic equation, done. Roots, done. Now we want to find the solution, which is the closed form of the sequence, the closed formula for the sequence, solution. So it's going to be of the form an equals alpha 1 times the first root, which we'll call 3 to the n power, plus alpha 2 times the second root, negative 1 to the nth power. So that's pretty much the form of your solution. You almost got your solution. All you have to do is figure out what alpha 1 is, what alpha 2 is. And we're going to get that based on the initial conditions. So I'm going to scroll down and I'm going to find alpha 1 and alpha 2. Where? Right here. Find alpha 1 and alpha 2. All right, so what were our initial conditions here? A0 was 1 and A1 was 2. So we're going to use our initial conditions to find these. Come on, dude. A0 was 1 and A1 was 2. All right, so let's write this down. We're going to create a system of equations. So 1 is equal to A0, and 2 is equal to A1. Now we want to apply this to our form of our solution. The form of our solution. So imagine here we have A0, right? A0. Imagine here that you plugged 0 in for n, 0 in for n back here, in the form of the solution. Yeah, so I plug in 0 for n there. And what I end up with, let's see, alpha 1 times 3 to the 0 power. Right, we're plugging in 0 for n here, plus alpha 2 times negative 1 to the plug-in 0 for n there as well, right? So I plug 0 in for n into my solution form, and then we want to go to the second equation where we're dealing with the a sub 1. So for a sub 1, we're going to plug in 1 into the solutions form. So we're going to have alpha 1 times 3, this time raised to the 1 power. Why? Because we're plugging in 1 for n. 1 for n. And then we're going to go plus alpha 2, this is not changing like it's supposed to, times negative 1 to the 1 power. Right, we're plugging in 1 for n into the form here, the form of the solution. So this is going to give us two different equations. Let's scroll a little bit. I'm going to go all into the single color here. So first of all, we have what? 1 equals. So with the first equation right here, we're just going to have what? Alpha 1 plus alpha 2. Why is that? Well, 3 to the 0 power is 1. Negative 1 to the 0 power is 1. The second equation, we're going to have 2 equals 3 alpha 1. And we're going to have minus alpha 2. Why minus alpha 2? Well, negative 1 to the 1 power is negative 1. So we're going to have negative 1 times alpha 2 is minus alpha 2. So we need to solve this system. We need to solve this system of equations. There are different ways to solve systems of equations. So what I'm going to do, I'm going to go to the side here. I'm going to basically add these two equations. I'm going to add these two equations. No, I'm not going to go to the side. I'm just going to add them directly. When I add them directly, I'm going to get, let's see, 1 plus 2 is 3. Alpha 1 plus 3 alpha 2 is 4 alpha 1. And when I add alpha 2 and minus alpha 2, those zero out. So we already have 3 is 4 alpha 1. So divide both sides by 4 and get alpha 1 is 3/4. That gives you one of your alphas. So for the other one, you can just plug back in, let's say, into the first equation. Now I'll go to the side here. So we're going to have 1 equals 3/4 plus alpha 2. Now if I subtract alpha, not alpha 2, if I subtract 3/4 from both sides, I get 1/4 is equal to alpha 2. So that finds me my alpha 1 and alpha 2 coefficients. So I'm going to go back up. I'm going to plug these in. So alpha 1 is 3/4, alpha 2 is 1/4. We're going to plug these back in to get our closed form of our solution. Finally, we're going to have what? AN is equal to, what was it? 3/4 times 3 to the n plus 1/4 times negative 1 to the n. So here we are. This is our final answer right here. I'm going to put a black box around it. This should be the closed form of the solution to that linear recurrence relation.